Hello, Statistics 200 students. Welcome to Lecture 10 in our Introduction to Statistics course series. Today we move into Lesson 5. We're moving away from probability and the descriptive statistics we briefly talked about. Now we're moving into probability distributions. But before we get started, here's a little bit of the joke of the day. And there are times where I've been asked questions that's really all I could think of to do as well, something like this. And sometimes you just have no clue to where to even start. So anyway, as I said, in this lecture, we're going to construct probability distributions, and we're going to do this by presenting possible outcomes along with the relative frequencies that we expect from those possible outcomes. So we'll start off with a review and preview, and then we'll move into probability distributions. I'm going to be jumping back and forth to Excel quite a bit here. I highly recommend that you take note of what I do in Excel because it will help you when you do the homeworks and the exams. So a quick review and starting the preview. This lesson combines some of the stuff that we learned from descriptive statistics. We learned from lessons 2 and 3 with those of the probability that was presented in lesson 4, the last couple of lectures. And it does this to describe and analyze probability distributions. Probability distributions describe what will probably happen instead of what actually did happen. That's what descriptive statistics do. So, descriptive statistics summarize data, summarize something that happened. Probability distributions talk about what probably will happen. They are often given in the format of a graph, a table, or a formula. Okay, in order to fully understand probability distributions, though, we first have to know a little bit about the concept of random variables. We need to be able to distinguish between a discrete random variable and a continuous random variable. And we'll talk about all three of these concepts in just a minute. So in this lesson, we're going to focus on discrete probability distributions. In particular, we're going to focus on the binomial and the Poisson probability distributions. This term right here is pronounced Poisson. When we get into lesson 6, we'll look at continuous probability distributions, the standard normal distribution, and then just the normal distribution by itself. Okay, so let's go ahead and move on. Now we're going to talk about probability distributions. Key concept about about this lesson, this section introduces the concept of a probability distribution. This gives a probability for each value of a variable that is determined by chance. What exactly does that mean? Well, let's not get ahead of ourselves, but that is, again, the key concept of this particular lecture. We're going to give consideration to distinguishing between outcomes that are likely to occur by chance and outcomes that are unusual in the sense that they are not likely to occur by chance. And we care about those because those can help us figure out whether later on our hypothesis tests are actually incorrect, whether we have an invalid hypothesis. Okay, we're going to start off with a couple of definitions. The first is a random variable. A random variable is some numerical value, value variable is typically represented by x that has, like I said, a single numerical value determined by chance for each outcome of a procedure. So each possible result of a procedure also has an associated probability with it. That's the determined by chance there. Excuse me. Now, a probability distribution is a description that gives the probability for each value of the random variable, often expressed in the format of a graph, a table, or formula. So random variable is a number. Probability distribution is a way to get a probability associated with every number in the random variable. Okay, so these two go together hand in hand. There are two types of random variables. There's a discrete random variable, which has either a finite number of values or it has a countable number of values. And by countable, I mean it can be an infinite number of values, but we can count each one individually. We can line it up with the number line. A continuous random variable has an infinite many values. Those values can be associated with measurements on a continuous scale without gaps or interruptions. So if you were to try to put these two in some kind of context, a discrete random variable would be the number of people in a room, or the number of people in our class. How about that? The number of people in our class is a discrete random variable. It's typically anywhere from 1, although they try to keep the classes at least 10 to make a section. So anywhere from 10 to the maximum class size for one of these classes is 32. Okay, so that'd be the discrete random variable. You can't have part of a person. You can have someone in the class that only participates part of the time, but you can't have part of a person enrolled. So either someone's enrolled or they're not. Okay, so our discrete random variable for the number of people in our class then, like I said, it's got to start at 10 for the class to go. So 10, 11, 12, all the way up to 30, 31, and 32. They cap the section at size 32. Gives me way too much grading if it goes beyond 32. Actually, 32 is a lot of grading as well. Clean that up just a little bit. Now, a continuous random variable, so the discrete random variable here x equals number of students in Stat 200, in a section of Stat 200. Okay, that is horribly written. But again, like I said, our random variable here, our discrete random variable, x equals number of students in a Stat 200 section. And it can be any of these values between 10 and 32. The continuous random variable, we would call this, I'm going to do it right above here, x equals the weight of all students in the Stat 200 section. Now, if you think about weight can always be, you can always add another decimal. You can always get more precise. You know, okay, you can say, hey, I weigh this much, all right? Well, you know, you on a scale, some scales have 1 decimal point, some have 2, some have 3. If you're trying to be very precise, then you can get on one that has, 5 or 6 values after the decimal point. All right, so that's a continuous random variable. We can always get more precise, and we can always add another value after the decimal, and that makes it to where it cannot be aligned directly with the integer number line. Okay, so that's discrete and continuous. Hopefully you understand the difference in those two. All right, there are a couple of requirements of probability distributions. The first is that there's a numerical random variable, which is x, and its values are associated with corresponding probabilities. Okay, so back on our previous one, we had the number of students, 10 to 32. Those are numbers. There's a probability associated with each of those. Okay, the weight of the students, well, that's a number between 0 and I don't know what a good weight would be for 32 people. I mean, let's say we all weighed 300 pounds, which is probably not likely. Is that 9,600? Okay, well, that's probably not going to be the case. Or is it? Yeah. So, but somewhere in there. Okay, so between 0 and 10,000 pounds. That's just a rough estimate. That's not necessarily all inclusive, but that's a decent range that we could have there. Okay. So, like I said, there's a numerical random variable x, and its values are associated with a corresponding probability. The sum of the probabilities must be 1. just like we have, or sorry, and if you think about this, think of it like a percentage. You can't actually give more than 100% of anything. Okay, 100% is the most you can give. So that's kind of what this is talking about. Okay, well, another way to write this is the sum, the probability of getting x for every 1 is equal to 1. Now the next requirement is that each value must be between 0 and 1, inclusive of those values. And that means that 0 is less than or equal to the probability of x, which is less than or equal to 1. So think about flipping a coin. All right. What's the probability of getting a head if it's a fair-sided coin? 0.5. What's the probability of getting a tail if it's a fair-sided coin? 0.5. Now, if you have a coin that's double-sided, has heads on both sides, then the probability of getting a head is 1 because they're the same. All right. So those are our probability distribution requirements. Excuse me. We can graph the results from a random variable or a probability distribution. We can graph something called a probability histogram. This is very similar to a relative frequency histogram, but our vertical scale here shows probability instead of actual count. Now, if you were to add up all this probability under here, then, if you were to find the actual value here for each of them and add that up, that's going to add up to 1. So again, the summation of the probability of each of my x's equals 1. So if you add up all of these probability values that you have here, it's going to give you 1. There are several equations that we're going to use to compute the mean, the variance, and the standard deviation for probability distributions. I'm just going to give them to you, and you're going to accept them on faith and not worry about having me derive them. The first is the mean, mu, which is equal to the summation of each individual random variable value x times the probability that you get that outcome x. Okay. The variance is a little more difficult equation. The variance, which is given by sigma squared, is equal to the summation of the value x minus mu, that term squared, times the probability of x. So this is giving you the difference of your current value from the mean and squaring it, so you will always have a positive value. So if you remember when we computed standard deviation before, we did this to make sure that we always had a positive value. Okay. So the shortcut for the variance, we looked at a shortcut for the standard deviation last time. Well, here's a shortcut for the variance, and you can use this or you can use the one up above. Either one is perfectly valid, but this is my variance, sigma squared, is equal to the summation of all of my x's squared times the probability of x, and then that entire quantity minus mu squared. Okay, and this is doing the summation of just these values and then subtracting the mean squared. Now the standard deviation, recall that standard deviation is just the square root of the variance. It makes sense. Sigma is equal to the square root of sigma squared. Logically, that makes sense. So all I'm going to do is I'm going to take the square root of this up here. So I have the square root of the summation of the quantity x minus mu squared times probability of x. And then the same thing for the shortcut formula. I'm just going to take the square root of that, put it down here. So I have sigma is equal to the square root of the summation of x, that term squared, times probability of x, minus mu squared. Okay, I'll give you a second to catch up on that if you haven't finished writing all that. These are equations. I'm not expecting you to know them. These are equations that you can use. Again, your assignments for your homework and your quizzes and your exams are open book, open note. But you need to know what the equations are, and you need to know how to apply them. So we're going to look at a few examples in just a little bit where you actually get to apply these. Okay. Now we talk about the mean, the variance, and the standard deviation here. Well, there's another term called expected value. The expected value of a discrete random variable is denoted by a capital E. It also represents the mean value. So it's the same thing as the mean. The expected value and the mean are the same thing. So unsurprising then, E, the expected value, is found by taking the summation of x times the probability of x. Okay, let's look at an example of how we would apply this, why we would apply it, what's going on here. Okay, so we're looking at 2 births, and we want to count the number of girls that occur in 2 different births. Okay, so, my sister had 2 kids. We want to count how many of those were girls without knowing what they were in advance. What's the probability associated with that? So remember, there are 4 outcomes of 2 births, right? There's boy, boy, there's boy, girl, girl, boy, and then there's girl, girl. Each one of these is equally likely. So each one has a probability of 1/4. Right? So boy, boy has 0 girls, and there's a probability of that of 1/4. Girl, girl has 2 girls. The probability of getting girl, girl is also 1/4. Having 1 girl, there's 2 different ways I can do that, boy, girl, or girl, boy. So if we add up 1/4 and 1/4, we get 0.5. Now, one of the requirements that we had for a probability distribution was that my probabilities had to sum to 1. Remember, requirement was summation of all my probabilities had to equal 1. So let's test it to be sure. 0.25 plus 0.5 is 0.75 plus 0.25 is 1.0. So yes, my probability summed to 1. So we're okay there. So now we want to find this value over here. This value is given by x times probability of x. Well, that should be pretty easy because we're going to multiply 0 times this probability of 0.25, which just gives me 0. You understand how I did that? I multiplied this value by that value, and it gave me 0. The next one here, this is going to be 1 times 0.5, which is going to give me 0.5. So that's my value here. I'll multiply these 2 values together. That's x times probability of x. And then for this last one, I'll multiply these. So I have 2 times 0.25, which is equal to 0.5. So hopefully you understand how I got those. I'm going to show you this a little bit cleaner now. So 0.0 is 0. We can just write it like this. 0 times 0.25 equals 0. For the next one, 1 times 0.5 equals 0.5. 2 times 0.25 equals 0.5. Now, recall what we're looking for to get the mean. The mean was given by the summation of x times the probability of x. Well, here we have x times the probability of x for each one of these, so we're just going to add down. So 0 plus 0.5 plus 0.5 gives me a mean of 1.0. So we understand how we did that? Okay, so let's see if we can do this next part on our own. I'm not sure if we'll be able to do it, but maybe we can. All right, so now I want to compute this value here. So x, which is 0, minus my mean, which is 1, that gives me negative 1. Here, I'll just write it all out. So 0 minus 1 squared times the probability of x, which is 0.25. So negative 1 squared is just 1 times 0.25 gives me 0.25. Okay? That one is pretty easy. That's just 0.25. For this next one, now we have 1 minus 1 squared times 0.5. Well, 1 minus 1 is 0, so 0 times 0.5 is just 0. So that one's pretty easy as well. Now we have 2 minus 1 squared times 0.25. See if I can write that a little better. 0.25. So 2 minus 1 is 1, squared it is still 1, times 0.25 is 0.25. So this term is just 0.25. So now to get my variance, I do the summation of x minus mu squared times the probability of x. Okay, so I've done this for each of my individual x's, so I just need to add down here again. So 0.25 plus 0 plus 0.25, think of adding 2 quarters together. That gives you 50 cents or 0.50. So here, sigma squared is equal to 0.50. Well, we want to find the standard deviation. So we have the mean and the variance here and here. How do we get the standard deviation? Well, just recall the standard deviation is the square root of the variance. So the square root of 1/2 is equal to 0.707. So there we have all of our values, and we work those out by hand. Now, I'm going to show you how you can do this fairly quickly in Excel. Right? This is easy to do it this way because these numbers were, they were small numbers that were easy to work with, except for maybe the square root of 1/2. I couldn't do that in my head. Now, here is our table that we were given, our x values and our probability of x. We can quickly compute x times probability of x here, and recall that we can drag this down, assuming that we do not have any cells that need to be pointed somewhere else. So that's okay, and that's okay. We also wanted to check first to make sure that our values, our probabilities sum to 1, and they do. And now we want to get the summation of x times probability of x, which we said was 1, and it is. So now we want to compute x minus mu squared times probability of x. So we're going to do x minus mu, okay, because this is summing down, so that's mu. We want to square that, and then we want to multiply that times the probability of x, which is this. Now, if we just drag this down, we're going to get an error here. Why? Well, because when Excel does this, when you grab a cell, and if you put the cursor right here in this corner and drag down, not move it, make it this little plus sign and drag it down, it drags down the equations and it copies them, but it keeps a cell reference relative to what we had just done. So here, this is telling, what we told Excel to do was take the value that's 3 to the left, that's what A3 is, 1, 2, 3 to the left, subtract the value that's over 1 and down 3 from it, square that, and then multiply it by the value that's 2 to the left. So it did that there. Now here, we're telling it again, find the value that's 3 to the left, multiply it by the one that's over 1, by the value that's over 1 and down 2, which is a word. Okay, well that's because we didn't want it to be this one. We wanted to fix on our mu value. So instead of doing it this way, we can come in here and we can say, okay, I want you to set this particular term right here, fix it at C6, which is my value for mu. To do that, we put a dollar sign in front of the C and a dollar sign in front of the 6. Now, when we drag this down, it's going to fix that cell right there for all of them. These, it went ahead and moved down like we wanted it to. But over here, that is fixed and stays there, which is what we want it to do. Okay, so now we want to find the summation of all of these, because again, we want sum of x minus mu squared times probability of x. So we just do sum of these terms, and that gives us our variance. We want to find the standard deviation. The standard deviation, again, is the square root. This is sigma, is the square root of the variance. So we can do that using the special term square root in Excel. And if you weren't aware of this, once you start typing an equation, if it's an equation that Excel knows, it'll bring it up here. If you click on that, it's going to open up Internet Explorer or an internet browser and go to a help menu, but we don't want that. But if you click on this fx right here, it brings up this function, embedded function in Excel, which helps you understand what parameters you need to use to get your answer. So this says, what this function does, it returns the square root of a number. The input is a number, is the number for which you want the square root. Okay, so we want the square root of that number right there. We could actually enter in a value here, or we could enter in a cell reference. So that gives us 0.707. Okay, so there we go. We just filled out this whole table that we did here. So that's our first example. Now, remember the range rule of thumb, which says that most values lie within 2 standard deviations of the mean. We should be able to identify the unusual values by determining if they lie outside the limits of the maximum usual value is mu plus 2 times the standard deviation, and the minimum usual value is mu minus 2 times the standard deviation. So we found for families with 2 children, the mean number of girls was mu equals 1.0, and the standard deviation was 0.707. Okay. We can use these values to determine the maximum and minimum usual values for the number of girls. The maximum usual value is mu plus 2 times sigma, which is 1.0 plus 2 times 0.7, which is equal to 1.0 plus 1.4, which is 2.4. The minimum usual value is mu minus 2 times sigma, which is equal to 1.0 minus 2 times 0.7, which is 1.0 minus 1.4, which gives us negative 0.4. Now, does it make sense to get a negative number here, or a number greater than our maximum value? Our numbers were 0, 1, or 2, and we have range that's outside of both of those, negative 0.4 up to 2.4. Well, yeah, actually it does make sense. This is saying that any one of our 3 numbers, 0, 1, or 2, are normal in this for this probability distribution, and that's perfectly fine. Okay, so that's a little cleaner way to show you the maximum and minimum usual value. Okay, let's identify some unusual results. There's something called the rare event rule for inferential statistics. This says that if, under some given assumption, the probability of a particular event is extremely small, we conclude that this assumption is probably not correct. So look at the case here. So let's assume that a coin is fair. Okay, and then we come out and observe 992 heads in 1,000 tosses of a coin. The probability of getting that is extremely small. So therefore, we assume that our assumption that we have a fair coin is probably not correct. Okay, there's probably something loaded about the coin. Okay, so probabilities can be used to determine when results are unusual. If we have X successes among N trials, this is considered an unusually high number of successes if the probability that we get X or more of these successes is less than or equal to 0.5. Sorry, not 0.5, 0.05. 0.05 is kind of a well-accepted range for or well-accepted value for determining when things are unusual. If we have less than a 5% chance of occurring, then it's probably unusual. Okay, X successes among N trials is unusually low if the number of successes if the probability that we get X or fewer successes is less than or equal to 0.05. Again, we're using the probability of 0.05 as our cutoff value to tell us that something is unusual. If we have a probability of 0.001, that's less than 0.05, so it probably doesn't occur normally, and we need to figure out what is causing it. Okay, now we're going to look at 3 examples. Actually, I'll do example 2 and 3, and then I'm going to let you do example 4 on your own. So for these examples, first we're going to determine if the data set is a probability distribution. Then we'll explain why it is or is not a probability distribution. And if it is a probability distribution, we're going to find the mean, the variance, and the standard deviation. If it is a probability distribution, we'll also find the minimum and maximum usual values. So the first example here. Dude, you ran that red light. So when conducting research on color blindness in males, a research firm formed random groups of 5 males in each group. So random variable X is a count of the number of males in the group who have a form of color blindness. And this data comes from the National Institute of Health. So what is this saying? This first one is saying that the probability that any particular group has 0 people in it with color blindness, that probability is 0.659. And the probability that any particular group has 1 person in it with color blindness is 0.287. The probability that any particular group has 2 people in it that is colorblind, has some form of color blindness, is 0.05. The probability that any group of 5 people, 3 of them have some form of color blindness, is 0.004. And in a group of 4 people, in a group of 5 people, the probability that 4 of them have some form of color blindness is 0.001. And in a group of 5 people, the probability that all 5 of them have some form of color blindness is 0.00. Now, it's probable that this value is not just 0. It's probably something like 0.000001, some very small number. But since they're only using 3 significant digits, these all go away, and you're just left with 0.00. So you're saying there's a chance. Yes, there is a chance that that could happen, but it's so small that it doesn't even register on this scale. Okay, so first question, is this a probability distribution? Well, what are the tests for probability? We have to have values for x's, each with an associated probability. What do we have to have for our probability of x? We have to have the summation of my probability of x's have to equal 1. Well, let's jump over to Excel and test that. Okay, so that was the first example. Here's our next example. So first thing we're going to do, we're going to type equals sum, and then we're going to highlight all these values. And that gives us 1.001. Now, you may look at that and say, hey, that's not 1, that's greater than 1, so this doesn't work. Yeah, that's not exactly the case. This does work. More than likely, what happened is we have a couple of these that rounded up, and when they rounded up, like this was 0.658, and this is 0.28, sorry, sorry, 0.6585, and this is 0.2865. Rounding them both up gave us this extra 1 on the end. So it's okay to be off a little bit there. A lot is not acceptable. A little bit's okay. So yes, this is a probability distribution Y. All random variable x's are values. The sum of our probabilities is 1. And again, that extra 0.01 is probably attributed rounding errors. And all of our probabilities are between 0 and 1, inclusive of those values. So now we're going to compute the mean and the standard deviation. And remember, the mean is equal to the summation of x times the probability of x, which we're going to sum up all these right here. And this variance, not the standard deviation, but the variance, well, no, I'll just write the standard deviation. The standard deviation is the square root of the variance, and the variance is the summation of all of these right here. So x minus mu squared times the probability of x. Okay, so let's jump over to Excel and compute this. This first one we can probably do fairly quickly. Actually, we already did this part, right? We already found the total 1.01. This one we can do really quickly. That's just 0.65, oh sorry, 0 times anything is 0. Now this one we can also probably do fairly quickly. 1 times 0.287 is going to be 0.287. Two times 0.050 is just going to be 0.10. That one's also fairly easy. Actually, these are all pretty easy. 3 times 0.004 is just 0.012. 4 times 0.001 is 0.004. And 5 times 0 is just 0. I cannot do that summation in my head, so we'll jump over to Excel to do that. But first, let me show you this, all those terms, in a little bit cleaner form. Okay, so let's jump over to Excel, and we're going to set this up again. This equals 0, or x, times the probability of x. Okay, recall again, I can drag this down. I just want to make sure that my cell references are correct. So here I want 3 times 0.04. That is correct. There I want 4 times 0.001. That is correct. I want to sum this down, so I'm going to say equals sum. I'm going to add all these. That gives me x, the summation of x times the probability of x, which is 0.403. So I'm going to come back here, 0.403. Okay, that's my value for mu. Now remember, we are now going to use this value. I don't know why it jumps that line like that. Sometimes we're going to use this value up in this equation. Okay, so that's the next step, is to put that into the equation. So we're going to jump over to Excel and do that here. This is equal to x, the value for x, minus my mu value, which is down here. Now remember, I need to put a parenthesis, not a parenthesis, sorry, a dollar sign in front of the C and in front of the 21 to fix this value, to fix this cell. So it always uses this value, 0.403. There's a couple different ways we can do it. We can manually put in the dollar signs, which we did before, or we can put our cursor somewhere on the C21 here. And if you have your function key, give your function lock, and you hit F4, then Excel will automatically lock that cell for you. All right, so then we want to close our parenthesis. We want to do the exponent, and if I didn't tell you before, to get this little exponent symbol here, that is Shift 6. That's called the caret key. So it's Shift 6. And then we want to square it, and we'll close our parenthesis again. And then we want to multiply that by the probability of x. Oh, it's telling me I have an error. What did I do wrong? Oh, I have an extra I don't have enough parentheses here. I need a parenthesis in front of this. There, now I have 2 open parentheses and then 2 closed parentheses. So that gives us 0.107. Okay, now we want to go ahead and drag this down, and we want to make sure that when we do, it keeps the cell reference at 0.403. So let's just look at one in the middle here. Yes, it's doing x minus mu, squaring that, and then multiplying it by probability of x. So we're okay there. So now we want to sum all of this to get, this is our variance here. So that's our variance. This is our mean, that's our variance. So what is sigma? Sigma, again, is the square root of the variance. So I'm going to type square root of that and then close the parenthesis, and there we go. All right, so now we have the values we need for our table. 0.107, 0.102, and 0.128. So 0.107, 0.102, 0.128. Okay, let's jump back. 0.027, 0.013, and 0. That's not a 6. That last value was a 0. And then we have our summation, which is 0.377. Okay, so I'll show you this a little bit cleaner. 0.107, 0.102, 0.128, 0.027, 0.013, and then 0. And then our sigma squared, which was 0.377. So what is our value for our standard deviation? It's right here. Sigma is equal to the square root of this, which is 0.614. So sigma equals square root of 0.377, which is equal to 0.614. So I'll let you take a quick second to get caught up on that. If you haven't caught up yet, go ahead and you can pause the lecture and then catch up. I'm going to go ahead and move on. Well, there's another way to get the mean, the variance, and the standard deviation. It's actually the same way, but it's writing it out by longhand. It's not as I guess pretty, it's not as organized, but it's the exact same function. So what is our mean? Our mean is the summation of x times the probability of x. Well, we can write that out. Make sure you get all of it. So remember, we had 0, and the probability of getting 0 people with color blindness was 0.659. We need to add having 1 person with color blindness, the probability of that was 0.287, plus probability of getting 2 people that are colorblind was 0.050, plus the probability of getting 3 people that are colorblind was 0.004, plus the probability of getting 4 people that are colorblind was 0.001, plus the probability of getting 5 people colorblind, and the probability associated with that was 0.000. We add all those up. Remember, 0 times 0.659 was 0. 1 times any number is that number, so we still get 287. 2 times 0.050, 0.010. 3 times 0.004 is 0.012. 4 times 0.001, 0.004. And 0 times 5 is still 0. All that gives us 0.403, which is what we found here, and that's our mean right there. Okay, so we can write it all out and solve it longhand as well. If we don't have Excel, we can do it longhand. We would also need to do the same thing for sigma. sigma being the square root of the sum, that's not a summation sign, the summation of x minus mu, that term squared, times the probability of x. Okay, well this is a really, really long equation. I'm just going to show it to you. You're more than welcome to take down this value, or to write it down. But remember, we did the exact same thing in Excel. So this is what it looks like. This here is all this part of the square root. So I have 0 minus the mean, which we found here, so that's the mean, times that probability squared, 0 minus the mean, square that, multiply it by the probability. 1 minus the mean, square that, multiply it by its probability, and so on. Okay, this is the exact same thing we did in our table, but you can work it out, you can write it out longhand like this as well. Gives us the exact same answer down here of 0.614. Okay, what are the maximum and minimum usual values? Recall our equation, mu plus 2 times sigma gives me the maximum usual value. What's my mu? It's 0.43. What's my sigma? It's 0.614. So, I just forgot what I said. 403 plus 2 times 0.614, which gives us 1.631, unless my math is wrong. Now, the min usual value then is going to be mu minus 2 times sigma, which is 0.403, minus 2 times 0.614. And I can't do that math in my head, but it comes out to be negative 0.825. Okay, let's look at another example. So Dave is not particularly creative, nor is he particularly smooth. He uses the same pickup line every time he goes out. His pickup line is, if I could rearrange the alphabet, I would put you and I together. All right. The random variable x is a number of times in a night Dave uses the pickup line before encountering someone who is interested, or probably better yet, encountering someone who doesn't throw a drink in his face, slap him, roll their eyes, or just walk away. So the first person he asks, the probability of having them respond, give a nice response, or a non-turning away and leaving response, is 0.001. His second try, if the first one fails, his second try is 0.020. His third try, if the first two fail, are 0.0105. His fourth one is 0.233, and his fifth one is 0.242. Okay, so I want you to find the mean, the standard deviation, the variance of this. So the first question is this a probability distribution? Well, let's jump over to Excel, because I have it down here. And let's do the sum of these probabilities. All right, so the sum of the probabilities is 0.601. So right off the bat, we know this is not a probability distribution. So why is it not? Well, first, all of our random variables are values. That's okay. That's the number of tries he has before he gets a positive response. But the sum of the probabilities is only 0.601. So there are clearly cases where it takes more than 5 times for Dave to get a positive reaction. So somewhere in there's a 0.3499 probability. So this could be down in the 10th, 11th, 12th chance before he's actually getting a positive response. So the recommendation here, Dave needs a new approach. Maybe he should try Match.com or get a new opening line. We do have all the probabilities between 0 and 1. However, because this one fails the test, we cannot do a probability distribution. We do not have a probability distribution, so we can't compute the mean, the variance, and the standard deviation. So here we said the sum was 0.601. So we do not compute the mean and the variance of that. We cannot do that. Same thing for the minimum maximum usual value. We can't do it because they don't exist in this case because it's not a probability distribution. So here's an example I want you to work on. Family time. Groups of people aged 15 to 65 are randomly selected and arranged in groups of 6. The random variable x is a count of the number of people in the group who say that their family and or their partner contribute most to their happiness. This is based on a survey from Coca-Cola. Okay, so I want you to take a look at it, and I want you to answer the questions that we looked at before. So first off, is it a probability distribution, and why or why not? So go ahead and pause the lecture and work through that. Okay, I'm going to show you the answer, so if you haven't paused the lecture, or if you're not finished, you need to pause the lecture. But here we go. Yes, this is a probability distribution. Why? All of our random variables are values. So here, all of our x's are values. We don't have an a or a b or something like that. The sum of the probabilities is 0.999. Okay, that missing 0.01 is probably attributed to rounding error. And all of our probabilities are between 0 and 1, inclusive of those values. So over here, we have all our values between 0 and 1. So this is a probability distribution. We're okay with that. So now we can compute the mean, the variance, and the standard deviation. Recall that the mean is the summation of x times the probability of x, and that our standard deviation is the square root of the summation of the term x minus mu squared times the probability of x. Okay, so you can go ahead and do that and check this and see if you can get this to work out. Go ahead and pause the lecture and work these out and see if you can get the values for the mean, the variance, and the standard deviation. All right, I'm going to tell you the answer now, so if you haven't finished, please pause the lecture. Otherwise, here's the answer. Compare your answers to my answers and see if you got the same thing. If you didn't, see if you can figure out what you did wrong, or if you think that I am incorrect, shoot me an email and I will double check my work. So minimum and maximum usual values. Again, the maximum usual value is mu plus 2 times sigma. And the minimum usual value is mu minus 2 times sigma. So go ahead and solve those. Pause the lecture if you didn't. Okay, I'm going to show you the answers now. So here's the minimum and maximum usual value. Maximum usual value is 6.674, and the minimum usual value is 2.556. Now this was a group of how many people? 6. A group of 6 people, and we have the maximum usual value, which is greater than 6. That's saying that getting 6 people would not be unusual. The minimum usual value is 2.556. So that's saying that getting 0, 1, or 2 would be unusual. And if you look at the values here, they are all less than 0.05, which is what we consider to be our usual values. And actually adding them up still gives us a value less than 0.05. So getting 0, 1, or 2 would be considered unusual. Sorry, not the probability that x equals 2 is unusual. Having x equals 2 would be an unusual result. Okay? All right, so that wraps up the lecture 10. I hope you enjoyed this lecture. I hope it helped enlighten you to explain more about probability distributions. In the next lecture, we're going to talk about the binomial distribution along with its associated parameters. Thank you for your attention, and feel free to email me if you have any questions. Have a great day.